Hello everyone. Welcome to episode 9 in the op-amp tutorial series, the inverting amplifier with offset and the differential amplifier lab demo. In the previous episode, we introduced and derived the transfer function for the inverting amplifier with offset, then used that equation to introduce and derive the transfer function for the differential amplifier. Today, we're going to demonstrate these two circuits in the lab with an LM324 op-amp. First, we'll take a look at the inverting amplifier with offset. Here we have the circuit schematic of the inverting amplifier with offset, along with the transfer function we derived in the previous video. And here's the demo circuit we're using today. The input is provided by a function generator with its intrinsic 50 ohm source resistance. The voltage of the non-inverting input, VA, is provided by a resistive divider between plus 12 and minus 12 volts, consisting of two resistors and two potentiometers. This allows me to adjust the VA voltage fairly widely to see the effect on the output. And the inverting amplifier has a 1.96 kilo ohm input resistor, a 9.81 kilo ohm feedback resistor, and is powered off of plus 12 volts and minus 12 volts. It also has a 1K resistor on the output connected to the negative 12 volt rail to ensure the output stage is always sourcing current so we don't get any crossover distortion. Rewriting the equation from the general inverting amplifier with offset and substituting in the resistor values, then simplifying, we get a gain of about 5.005 for the input voltage, Vin, and a gain of about 6.005 for the offset voltage, Va. We'll monitor the input voltage with scope channel 1, the output voltage with scope channel 2, and the offset voltage, Va, with a digital multimeter. Now let's move over to the lab to see this circuit in action. Here we have our circuit setup. On the left is the isolated plus and minus 15 volt power supply board, which flows to the breadboard's plus and minus 12 volt regulators shown on the right. Zooming into the breadboard, we see the plus and minus 12 volt regulators on the top, the inverting amplifier circuit, the resistors and potentiometers that make up the offset resistive divider in the middle, the function generator positive input on the input to the inverting amplifier circuit, scope channel 1 connected to the function generator positive input, scope channel 2 connected to the output of the inverting amplifier circuit, and the DMM on the non-inverting input of the op-amp. So everything's powered up, and we set the function generator to 100 Hz, then enable it. There's some EMI on the input from external unrelated sources, so I'm using the averaging feature of the oscilloscope to reject the noise to clean up the signal. We see here that the input is zero-centered and sitting at around 316 millivolts peak to peak, with the output at around 1.56 volts peak to peak, with the non-inverting amplifier input at very close to 0 volts. This is a gain magnitude of approximately 4.937 volts per volt, which is pretty close to our expected value of 5.005. We see that the amplifier inverts as expected. Now let's add some offset to the input using the function generator. First, I need to disable the scope's averaging function so that the display updates more quickly. Moving the function generator's DC offset up causes the output to go down as expected. Now let's increase it to the point where the output is saturated, and the DC offset far exceeds the magnitude of the actual sine wave we're interested in. Now we can change the offset into the non-inverting input by adjusting the potentiometers to bring the output signal back into the power supply range and stop it from saturating. So let's adjust the voltage on the non-inverting input, which is being monitored by the DMM on the left, until the output is approximately zero-centered, and see what voltage was required to do that. So the average voltage on the input is about 2.44 volts, which is also the DC offset. This means the output is attempting to amplify 2.44 volts by negative 5.005, which is about negative 12.21 volts. In order to negate that, we need to set the output offset equal to positive 12.21 volts, and so the input offset, VA, needs to be 12.21 volts divided by 6.005, which is about 2.033 volts. Experimentally, we get a voltage of about 2.09 volts, which is pretty close to our predicted value of 2.033 volts. So we've shown that we were able to use the amplifier's non-inverting input to negate a large DC input offset, so we could amplify up a small signal riding on top of it. Moving on, here we have the schematic diagram for the differential amplifier as introduced in the previous video. Now we put some real values for the components. This is the first differential op-amp circuit we will be demonstrating. The differential input to the circuit is provided by a function generator into a transformer with a center tap on the output. This converts the function generator's single-ended output to a differential output. I have not measured the turns ratio for this transformer, but it won't matter because the secondary of the transformer will be our input voltage measurement. The center tap is being controlled by a resistive divider made with resistors and potentiometers, similar to the one for the inverting amplifier with offset circuit. This allows us to control the DC offset of the two output voltages, while still keeping the differential output voltage unchanged. There is a rather large 100 microfarad electrolytic decoupling capacitor there, along with some higher frequency ceramic capacitors not shown. This is necessary because the AC impedance of the offset generation circuitry is way too high, and without that capacitor, the center tap would move around because of the unequal currents flowing out of the two sides of the transformer. The four resistors are made up of static 5% resistors, as well as a potentiometer that I use to make small adjustments to ensure that the two dividers are well balanced, and so the circuit has a much higher common mode rejection ratio than it would have had I only used 5% resistors. Though it is worth noting that the temperature coefficient of 5% resistors is generally pretty high, so it's probably not as well balanced now as it was when I first calibrated it. The differential gain produced by this circuit is approximately 9 volts per volt. Finally, as with the inverting amplifier with offset, I've put a 1 kilo ohm resistor on the output to negative 12 volts to eliminate the kind of crossover distortion we saw in episode 2 by ensuring that the output of the amplifier is always sourcing current. Here we have a wide view of the setup, with the plus and minus 15 volt power board connected to the breadboards with plus and minus 12 volt regulators, as we did previously. Zooming into the two breadboards, we have all the parts of the circuits labeled, with the input side circuits like the transformer and offset divider on the left breadboard, and the differential amplifier on the right breadboard. We start with scope channels 1 and 2 connected to the positive and negative differential input signals, and the DMM is monitoring the DC offset at the center tap of the transformer. Setting the function generator to 5 kHz and enabling it, we see the two sine waves 180 degrees apart from each other appear on the screen. They are very close to a 0 DC offset. As you can see, the average voltage for both channel 1 and channel 2, which is the same as the DC offset if you have an integer number of waveforms in the screen, is around negative 20 to negative 30 millivolts, which is pretty close to what's measured by the DMM there on the left. So let's adjust the potentiometer to change that offset. And we can see that the two waveforms move down when the offset is made more negative. Here the DMM shows about negative 600 millivolts, and the average voltage of the two channels is about negative 620 millivolts. So there's a small offset between the two measurements, but it's pretty close. We can also move the offset up, and we get similar results. Now that we've shown that changing the potentiometer changes the common mode voltage of both waveforms equally, we'll move scope channel 2 to the output of the differential amplifier to see how the output is affected by the changing common mode voltage. And we see the output voltage here is approximately zero-centered. The voltage is a bit lower than we predicted with a gain of 9, but I'm not confident in the accuracy of those resistor measurements. I may have adjusted them after I measured them, so I'm not surprised that the gain is off by a bit. When we move the input offset voltage up or down, the output doesn't change, so this circuit is very effectively rejecting the common mode input voltage. One final thing to note about this circuit is what happens when I remove the output resistor. Recall that crossover distortion occurs when the direction of current out of the op-amp changes direction. Current out of the op-amp doesn't only go into the load, it also goes into the feedback path to enforce the virtual ground. Here I remove the output resistors, and we see the crossover distortion return. Now when I move the input common mode voltage up and down, we see the point in the waveform at which the crossover distortion occurs also changes. This is happening because the input common mode voltage is changing the virtual ground point, and that in turn changes the point on the output waveform at which the op-amp's output current is switching direction. So I chose a load resistance that was much smaller than my feedback resistance to compensate for this effect. To demonstrate more practical benefits of this circuit, we have to make a slightly more complicated system with a source of interference to reject, as well as circuits that generate a signal and create both a single-ended version and a differential version of that signal. Here's a block diagram of the system. There are two breadboards in the system with about a half a foot of cabling between them. The idea here is that we have a temperature sensor on breadboard 1 on the left, and we would like to transfer that signal to breadboard 2 on the right in the presence of a switching load on breadboard 2. Let's look at each piece of this circuit in a little more detail. We have a plus 15 volt power supply coming into a positive 12 volt linear regulator and ground, which provides power to breadboard 1. It is transferred over this twisted pair of wires to breadboard 2, where it provides power to the circuits on breadboard 2. We also have a negative 15 volt power supply coming into a negative 12 volt linear regulator and ground, which provides power to breadboard 1. It is also transferred over a twisted pair to breadboard 2, where it also provides power to the circuits on breadboard 2. The board providing the plus minus 15 volt power rails is isolated from earth ground. Though it has some parasitic capacitance to earth ground, it will not matter for this demonstration because we will be dealing only with DC signals. Moving down, we see that the point at which our signal of interest is generated is this small current source flowing into a thermistor generating a voltage. My DMM is connected to the thermistor voltage and a nearby ground so we can monitor the true signal voltage. This voltage is then buffered by a unity gain buffer op-amp circuit, then transferred to breadboard 2 with ground over a twisted pair. The resulting single-ended signal on breadboard 2 is then amplified by a factor of 18 with a non-inverting amplifier before being connected to oscilloscope channel 1. This is the single-ended path. In parallel with the single-ended path, we have the differential path. Here our signal is converted to a differential signal before being transferred to breadboard 2 using a differential pair. Once on breadboard 2, the differential signal is converted to a single-ended signal using the differential op-amp circuit we discussed in the previous video, which is shown in the blue box. The differential signal undergoes an amplification by 9 before being output to oscilloscope channel 2. Since the conversion from single-ended to differential effectively introduced a gain of 2 into the chain, the resulting signal level on scope channel 2 is the same as the single-ended result on scope channel 1. So if there is no interference, those two channels should be identical. Finally, we have at the bottom here a 750 milliamp current source that has a 2 volt compliance. I generate this signal using an external power supply which is isolated from earth ground, though again there's parasitic capacitance to earth that is immaterial as we are only operating in the DC regime. The current source is connected to a single wire from breadboard 1 to breadboard 2. I haven't used a twisted pair here, though we'll see in a moment that a twisted pair would not help protect the other circuits from DC interference by much. Once it's on breadboard 2, it's connected through a switch to breadboard 2's local ground. Now let's think about current flow through the ground in this system. So looking first at the plus 12 volt rail, we see that anything on breadboard 2 that draws power from the plus 12 volt rail and goes into ground will flow from the plus 15 volt source, where the top blue arrow is, into the regulator out through the plus 12 volt line, into breadboard 2, then through whatever loads to ground are there, then flow back to breadboard 1 through all of the ground lines that connect breadboard 2 to breadboard 1, then back into the plus 15 volt source through the bottom blue arrow. The important note here is to recall that the current flows through all the grounds, not just the ground in the twisted pair, carrying the plus 12 volt power line to breadboard 2. Fortunately, most of the current in breadboard 2 is the supply currents of the op-amps, which flows from plus 12 volts to minus 12 volts. And so there aren't any significant ground currents, as the supply current flows from the plus 15 volt rail through the path colored in red, then back through the minus 12 volt rail through the path colored in gold. The signal currents from the single-ended wire and the differential wires are so small in this situation as to be negligible, and indeed the power currents we just mentioned that go to breadboard 2 are also very small. The problem occurs when a relatively large current is switched on, and the voltage drop across these ground wires become non-negligible. The voltage drop across ground means that the ground on breadboard 2 is actually slightly higher voltage than the ground on breadboard 1. Since the signal's ground reference is on breadboard 1, When it's buffered and transmitted single-ended over to breadboard 2, the signal voltage with respect to breadboard 1 ground does not change. However, with respect to breadboard 2 ground, the signal appears to be of a lower magnitude. This is the corruption that the EMI of this large switching current causes to the single-ended signal. It is not present in the differential signal since both sides of the differential signal are corrupted in the same way, and so that corruption is rejected by the differential amplifier on breadboard 2. Now let's take a look at this circuit in the lab on the oscilloscope. Here we have our test setup. Very similar to the two previous test setups, we have our plus and minus 15 volt power board on the left and the two breadboards on the right, with the 750 milliamp current source provided by my power supply in the upper right. Taking a closer look, we see the two breadboards as shown in the schematic. The left breadboard contains plus and minus 12 volt regulators, the unity gain buffer for the single-ended circuitry, the single-ended to differential conversion circuitry, and the thermistor and its biasing circuitry that make up our signal source. The DMM is connected to the thermistor and near its own ground so as to allow the DMM to show the true signal we're trying to measure. The wires between the two breadboards are the two power twisted pairs and the two signal twisted pairs. The right breadboard contains the single-ended amplifier and the differential amplifier, as well as the two oscilloscope channels. Oscilloscope channels 1 and 2 are connected to the output of the single-ended amplifier and the differential amplifier output respectively, with their grounds connected near where the ground for Vout single-ended enters the right breadboard. Finally, I've noted the red and green twisted pair with the common mode choke as the wires for the 750 milliamp current source coming from my power supply. The current source comes from the power supply, flows through the twisted pair through some common mode chokes to reduce the noise coming from the power supply itself into the left breadboard's ground line. But the power line from the current source plugs into this yellow wire, which is fed to the right breadboard's ground, and the switch is just me physically inserting and removing the wire, thereby closing and opening the switch. So here we are with the whole system powered up. The DMM shows that the signal voltage is about 340 millivolts, and on the scope we have channel 1 in yellow showing about 6.14 volts, and channel 2 in blue showing about 6.14 volts. This is very close to what we expect, since the single-ended channel has a gain of 18, and 18 times 340 is 6.12 volts. And the differential channel has a total gain of 18 as well. Since the conversion to differential effectively produces a gain of 2, then the differential amplifier has a gain of 9. Here I'll just touch the thermistor to heat it up a little bit to see how the output voltages change, and heating it up from 340 millivolts to 360 millivolts produces an output voltage from 6.14 volts to around 6.5 volts. So a 20 millivolt input voltage difference results in a 360 millivolt output voltage difference. This is exactly what we expect since 360 is 18 times 20. Now removing my finger, we see the voltage drop down as expected since the thermistor is getting closer to room temperature, and it is a positive temperature coefficient thermistor. Now I short out the current source with this yellow wire on the right breadboard, and we see it draws 750 milliamps. Looking back at the scope screen, we see that the signal voltage is back to around 340 millivolts, and the differential signal is still at 6.14 volts. But the single-ended signal is now at about 5.78 volts, a drop of around 360 millivolts. So the differential signal is rejecting the difference in ground voltage between the two breadboards, but the single-ended signal is not. When I open the circuit so that the 750 milliamp current source shuts off, we see the single-ended voltage in yellow returns to its previous voltage of about 6.14 volts. So we have shown that a relatively large current can interfere with other circuitry even at DC, and differential signaling can mitigate problems like that. At DC, the voltage differences are caused by the finite resistance of the wires, but at higher frequencies, inductance will come into play. Interestingly, whether or not high frequency makes the interference worse is very dependent upon the setup. If the interference source is a twisted pair of wires, with one being the power signal and the other being the ground, then at high frequencies, the ground path in the twisted pair will have a pretty low inductance. However, if the twisted pair happens to be physically longer than the other ground paths, then the overall inductance may not be lower than those separate ground paths. And of course, not all power signals can be twisted pairs. EMI is a complex field of electronics, and an in-depth study of it is beyond the scope of this video. It deserves some separate consideration in future videos. That concludes this episode. In this episode, we did lab demos of the inverting op-amp with offset and the differential amplifier circuit. In the next episode, we will be introducing the non-ideal op-amp. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. See you next time.